So when you're lacing a hub motor into a rim to build your own wheel, one of the really critical details that you get right is the length of the spoke. That length, of course, depends on which specific model of hub that you're lacing and how big your rim is. Now, there are lots of tools that are out there for measuring or calculating spoke lengths, but most of these spoke calculators were really meant with normal bicycles in mind. So what we did is created a spoke calculator specially optimized for the specific nuances of hub motor wheel building, and we're going to share with you the details of how to use our spoke calculator tool. This tool is available from our website. If you go to the Tools menu and in a drop-down, you'll see Spoke Calculator. Click there, and here you are presented with Grin's hub motor spoke calculator. Now, this window is divided into three main sections. So on the left side are all of the input parameters for setting the details of your hub, your rim, and how you want the lacing to be done. The middle here shows a really nice real-time preview of what the built-up wheel is going to look like. So you can see, side view, what the crossing pattern looks like, the kind of angle you have between the spoke and the rim, as well as a cross-section view where you can see the angles, kind of the triangulation of the spoke, and how the dishing offset's done on the left and the right side. And then at the very bottom, you get the actual output. What is the left spoke length, the right spoke length, so that you can order the spokes of exactly the right size, plus the numeric value for that spoke angle and the relative tension of the left and the right spokes. So now we're going to go into some detail on how to choose the right settings for the wheel build that you want to do. So starting off with the hub, we've got a large number of hub motors already modeled, and they're all available by just clicking this drop-down link. So if you're doing a wheel build and you happen to be using a motor that we've already characterized, you can just pick that motor from the list. It will automatically pre-populate these additional parameters. If the motor you got isn't here, don't despair. It's really quite easy to measure and input these values directly. So we've created, Robert, our wheel builder, has made a great video detailing how you can make these measurements at home without any fancy measurement equipment. And I'm just going to go over one by one what each of these values are. If you are on our website itself, you can also get this information just by hovering the mouse over, and you'll see this little tooltip pop up that gives a more detailed explanation. So starting off is the flange diameter, and this is the most critical detail for the hub itself, and that's really the diameter from one spoke hole to the center of the other spoke hole on the opposite side of the flange. And we call this out in the drawing. You can even see the flange spacing, flange diameter, referenced on the preview drawing itself, and you can see what it is that you're measuring. Now, the flange spacing is visible in the cross-section view, and that's the spacing between the left flange and the right spoke flange. So a lot of hub motors, especially direct drive hub motors, have flange spaces that are quite narrow together. Geared motors tend to have wider flange spacing because the hub itself is wider, and that flange spacing affects the amount of triangulation that you get with the spokes, which can affect the strength of a wheel build. Now, the dishing offset is another interesting parameter, and that is the relative distance of the center between the two flanges and the actual center of the wheel. Now, some hubs are perfectly symmetric and they have no dishing offset, but more often than not, what you'll find is that a rear hub motor has the flanges shifted over to the left side, and that's to make room on the right for the cassette-free hub. And on a front hub motor, the dishing offset's often in the opposite direction, and you'll see that it is shifted to the right so that you have room on the left for mounting the disc caliper. The number of spokes, of course, needs no explanation. Most hub motors are 36 spokes. Most bicycle wheels are 32 and sometimes 28 spokes. There are some fancy hubs that use 48 spokes or even 72 spokes. Our spoke calculator is extremely forgiving here. So if you wanted to do a 365 spoke wheel, well, it would do its best. Not being a multiple of 4 is a bit of a limitation. And of course, the number of spokes has a very significant effect in the length that you get because the angles change. So 36 is the common for most wheels. And then we've got a few other parameters here, like the axle length. This really doesn't have any effect on how long the measured spoke is. It simply affects the drawing that you see on the right, and it helps you make sure that your visualization is a little bit more accurate. So a front hub with a 100mm axle shows that being shorter. Now, the hole diameter, this is the diameter of the hole through which the spoke hole goes. This doesn't have a huge effect on the spoke length, but it does have a minor effect because the spoke length is measured not from the center of the spoke hole, but from the very edge where the bend of the spoke is pressed up against. So if you have a larger spoke hole, then the spoke lengths will be a little bit shorter because the spoke is sitting a little bit closer to the rim. Now finally, the last option here for paired spoke holes is something quite special and unique to our spoke calculator, and something that's really important with hub motors. And in a normal bicycle hub, universally the holes are just evenly spaced around the flange, and the spokes are crossed in order to get a desirable angle from the spoke to the rim. Hub motors have a much larger diameter, and crossing the spokes often becomes problematic, especially when you have a small rim and a large flange. It results in a very acute angle between the spoke and the rim. So the motor manufacturers have addressed this by creating an uneven spacing between these holes. So instead of them being uniform, they might space them close together, and so every two holes are close, and then there's a large gap to the next hole. And this has an enormous benefit in wheel building in that it allows spokes that don't have any cross pattern to still have a spoke angle. Normally, historically, with existing spoke calculators, it's nearly impossible to get a spoke length calculation when your spoke holes are paired this way, but we've made it really easy in our spoke calculator tool by simply measuring the distance between the two close holes that are paired together and putting that number in millimeters right in this value. So a closer pairing, you see those holes are closer together. And if you uncheck the paired spoke holes, then it will go back to being a uniform distribution. Okay, so now we'll talk a little bit about the rim settings. So when you have a rim, there's really one critical measurement, and that's the ERD, the effective rim diameter. So when you're measuring diameters of rims are notoriously referencing nominal dimensions that don't exist in reality. So if you have a 26-inch rim, there's no measurement on this rim that's 26 inches. That's the diameter of the tire that fits around the rim. There is a measurement for the outer rim width that is very relevant for tire sizing, but when you're building the wheel, it's the inside of the rim that matters. So if you have a rim that's very deep, then you have shorter spokes. The ERD is the measurement from where the end of one spoke theoretically should fit relative to the end of the spoke on the opposite side of the rim. So crudely speaking, it's sort of an inside diameter measurement of the rim, but to get this exactly, you want to know how far into the rim the spoke head protrudes. And once again, Robert's video governing how to measure these things at home shows how you can measure this with nothing more than a tape measure and a spoke nipple as a reference. So that's the essential value, the ERD. The left and the right offset is important, especially when we're dealing with fat bikes or rims that are quite a bit wider. And you'll often see that in those cases, the left and the right spokes are not evenly positioned down the middle of the rim, but they're staggered with an offset between them. So with this tool, you can give the stagger for the left spoke offset as well as the right spoke offset independently. And that will then, of course, shorten the spokes and result in less spoke triangulation. The rim width value here is just for drawing purposes. If I make this a lot wider, you can see the sketch of the rim changes its width, but it doesn't change any of the spoke measurements, of course. That's just a cosmetic detail. So now is where things get a lot more interesting. The parameters for the rim and the hub are, of course, fixed measurements. You can't change that. But when it comes to lacing the wheel, there's actually quite a few different ways you could lace a given motor to a given rim. So you have a choice in the crossing pattern between the spokes. You also have a choice in how you position the elbows of the hub. Some of those choices require some advanced knowledge of the specific motor that you're building. So the cross pattern, of course, is how many times the spokes cross over each other. Radial crossing, or zero cross, means the spokes don't cross at all. This is by far the easiest way to lace a wheel. If you don't have paired spoke holes, it means that the spokes all sit totally perpendicular to the rim. So there's a 90-degree angle between the rim and the spoke. And if the motor's trying to transmit torque, if it's trying to spin, the spokes all have to flex over a little bit and produce a little angle there in order for that torque to couple to the rim. What that means is that every time you power the motor and release it, the spokes get stretched and relaxed, and that constant cycling can cause the nipples to get loose quite quick and result in a wheel with loose and broken spokes. So it's normally not desirable to have a radial lacing when you have even spoke holes. Now when you have a paired spoke hole situation where the spokes aren't evenly spaced, then that radial lacing, as you can see, still results in an angle between these two things so that torque can be transmitted. So zero cross lacing is great with paired spoke holes. Normally, you'll be using a single cross with a hub motor build. So for most rims and most hubs, that results in an appropriate degree of angle between the spoke and the rim. If you were to go to a higher cross pattern, like a double cross on a motor like this, you can see that the spokes are at quite an acute angle with the rim. And if you have less than, anything less than 75 degrees, it gets really difficult in order to feed the spoke into the nipple. And as you tighten it up, you're then going to get a sharp bend at the spoke right where it goes through to the nipple, potentially resulting in a weak point right where the threads start. So we recommend choosing a lacing pattern that results in 75 degrees or greater for this spoke angle here. And in cases of a really small diameter hub and a large rim, like a 700C rim here, a double cross spoke works pretty well, but most of the time you're going to be doing single cross or radial if it's paired spoke holes. Now you notice that with a single cross, there's actually two options. Same with 2 and same with 3. We've got the single cross and the single cross alternate, double cross and double cross alternate. So this is a specific choice when it comes to motors with paired spoke holes. So if I go back to a larger diameter wheel with paired spoke holes, here I've got the regular single cross, and in this case they cross over the narrow gap between the paired holes. If I choose the 1 alternate, then it does the wheel build simulation where we cross over at the wide gap. There are a few cases where this is a useful feature to take advantage of. One of them is if you happen to have spokes of a given length and you want to see if they can be used in your wheel build, but it also gives more flexibility in choosing a cross pattern for your desired angle there. Next up, we have the position of the elbows. So we have an option for the spokes to come through the flange with the elbows on the inside of the flange or the elbows on the outside of the flange. And this is a good example here where you can see that the spokes on the left side here have the elbow inside the flange, and the spoke is almost vertical. And if you have a spoke that's almost vertical, it has very little ability to provide triangulation strength to prevent the rim from buckling. And it results in a much higher share of tension in that spoke than the other spoke. So if you look in this particular build, we've got a tension ratio of 70 to 30. So most of the tension is on this left side, and that results in more likelihood of spoke breakage. If we flip this spoke so that the elbow's on the outside of the flange, then we can see we now have a much more consistent angle between the two sides of the spoke, and our tension ratio is much closer, 58 to 42. So in general, if you have a hub motor where the flanges are close together, you usually want to put the elbows out, and that widens the base of the spokes, and that gives you a better triangulation, and that results in a stronger wheel that's less likely to buckle if there's significant side loadings. But there's some cases where this isn't desirable. One example would be if you have, for instance, the GMAC hub motor. This is a great hub motor, but in the design, if you lace it with the elbow on the outside, the elbow protrudes a little bit from the flange, and it's just enough that the derailleur on a lot of bicycles risks rubbing against the spoke elbows as you're biking when you're in your largest gear. Some motors have a similar problem on the disc side where the elbow on the outside will then interfere or rub against certain disc calipers. So if that's the case, you have no choice but to put it with the elbows on the inside. Now in most conventional wheel building where you do a triple cross build, people alternate one spoke, one elbow in, one elbow out, one elbow in. There's no advantage at all to doing that on a hub motor build when you're only doing a single or a double cross. It's usually beneficial just to have all the spokes going in from the same side to take advantage of either maximizing the triangulation or minimizing the interference. Now, the hub shift that we have down at the bottom is a useful feature if you're adding spacers to the hub motor. So there's quite a few situations in e-bike motors specifically where the stock motor might say only be designed for a 5-speed freewheel and you want to put on an 8-speed freewheel. In order to do that, you need to add spacers to the axle. But those spacers on one side of the axle cause the entire hub to shift over in the other direction once you mount it in the bike frame. So if you, for instance, wanted to put a 5mm washer on the right side in order to put a larger freewheel assembly on there, you would want to shift the center point of the wheel 2.5mm to the left. So in that case, I would put a negative 2.5mm hub shift, and then this now biases the motor in that direction so that once you put your spacers on here, you're now lacing it up to a truly centered wheel. There's also cases where you put spacers on the disc side in order to get a better alignment of the disc rotor to a disc caliper. These movements of a few millimeters you might not be too fussy about, but sometimes it puts you in a threshold where you might want to order a slightly longer spoke on one side than the other side as a result of shifting it to account for this new position. And the last feature that we have here is the swap spokes checkbox. Now this was something we made originally for a kind of unique problem. And that problem happened when people had a hub motor, a direct drive hub motor with flanges that were close together, but they chose a rim, a fat bike rim. Let me see what we have on this list for a fat bike rim. There we go. Actually, let me put a 20-inch on there. And here you can see that because of the stagger on the fat bike rim, and in some cases it's even, most fat bike rims have even worse stagger than this, what you have is spokes that are nearly vertical. And if you have a wheel build with the flange and the rim spokes just line up like this, you have zero ability to actually tension and true the wheel properly because you're not able to pull the rim to one side or the other. So the whole principle or premise of wheel building requires this triangulation so that you can tug the rim one side to the other side and then get it so that it's perfectly centered on the frame. So we introduced this swap spoke so that you could actually interchange and have your right spokes go into the left holes on the rim and the left flange spokes go to the right holes of the rim. And that results in the spokes now being triangulated instead of nearly vertical. On paper, this seemed brilliant. We were quite excited to then be able to offer a lacing option for these fat bike motors, fat bike rims in the hub motors with the narrow flanges, but we actually found in practice it's nearly impossible to true a wheel when you cross them to this extreme measure. But if you have a case where the left and right offsets are quite a bit closer, then it can be a useful trick if you have a case where there's not quite enough triangulation, and that just slightly increases the triangulation, especially if you're dealing in one of these cases where a spoke's nearly vertical. So those are some of these more advanced tweaking options that you don't normally see in a spoke calculator tool, but it's a great idea to visualize and see this and sort of plan out your wheel build in order to have the best chance of a strong, robust lacing job. So one thing that if you're astute, you may have noticed is that every time I change these settings in my spoke calculator, the URL on the top of the browser was updating as well. And what this does is it keeps a record of all the special parameters that I've put here so that you can copy that and then email that to somebody. You can email it to us. If we paste that same information into a new browser window, here is a less optimized spoke calculator. We'll override that with Grin's. It will then load the exact same motor details. This makes it really useful for communicating. If you have questions for us, if you've made the right choices in the spoke build, and you can also keep your own local record on how you came to the conclusion for a certain spoke length. This also lets us do something a little bit clever. If you're somebody who has your own list of hubs that aren't in here, for instance, you could fill out the details of your non-Grin drop-down hub, and as you do this, you get all that information in the URL. You could just make a bookmark of this, and then whenever you open that bookmark, it'll have pre-filled out the details for your own custom hub, and then you can just pick and choose the rim and the lacing pattern and not have to re-enter this information every time that you want to use it. Now with every input explained, we hope that helps you navigate through our spoke calculator so that you can figure out just what length spokes you need. When it comes to ordering those spokes, of course, you can order that from our website. We sell almost exclusively SAPM spokes that are single-butted. They're 2.3 millimeters or 13 gauge at the elbow, and then they taper down to 2 millimeters or 14 gauge at the threads in the nipple. For e-bike hub motors, we find that this is pretty much the perfect spoke. Most of the hubs are drilled out for 12 or 13 gauge spokes, so it's a larger hole in the flange than you get on a normal bicycle hub. Now, if you have a straight 14 gauge spoke, which is the standard that most bicycle shops carry, that 14 gauge spoke usually won't have a head that's large enough to seat properly against that hole. In fact, sometimes the spoke will just pop right through the hole in the hub motor flange. So these butted spokes have a larger head so that they fit in the flange properly, but then they accommodate standard 14 gauge nipples at the rim side. And that's really important because most quality bicycle rims are eyeletted and they're sized for 14 gauge nipples. If you have a 12 or a 13 gauge spoke, those need a larger diameter nipple, and they're not actually going to fit in the hole in your rim unless you drill out that hole to be larger, which of course is not doable if your rim has eyelets punched into it. We also find that there's no benefit to heavier gauge spokes. There's a bit of misinformation out there. A lot of people have problems with spoke breakage in hub motor applications, and that's almost all a result of poor wheel building technique. It's really not a limitation of the diameter of the spoke that you're using. When you think about it, people doing off-road heavy mountain biking, they just have 32 spoke hubs. Everything is straight 14 gauge. They're doing massive drops and not breaking spokes at all. Those forces are much more significant than the sort of steady constant torque that a hub motor puts on a wheel. So stick to standard bike rims with a 14 gauge nipple and follow Robert's excellent wheel building video, and that will detail how you can take this information, lace that wheel at home, do it like a pro, and have a wheel that lasts for years and years without ever wobbling, going off true, or suffering a broken spoke. I'd also like to just thank the two co-op students who helped realize the spoke calculator. We had initially had just a very simple HTML form spoke calculator in the early days of ebikes.ca, but I always wanted a more visual tool with a lot more dynamic calculations, and both Sanjaya and Samsung were two co-op students who we had here at Grin many years ago, and as part of a summer co-op term managed to create this whole real-time dynamic display, which, as you can see, has now close to 600,000 spoke calculations. We imagine, tens of thousands of people all over the world have made use of it. So thank you for helping us put this together and make this available to everyone.